Analytical. This flowchart illustrates how nearly every modern building operates. We build our cities on a linear system. We extract materials, assemble the shell, constantly drain external energy to keep it habitable, and eventually send the debris to a landfill. Most of a building's environmental impact occurs before anyone moves in. Zooming in on the construction phase, this comparative bar graph reveals the carbon footprint of standard materials. Cement production alone produces a volume of emissions that dwarfs renewable alternatives. Daily operations are equally inefficient. Shifting to the lifespan node, this thermal diagram shows a standard building radiating heat in the winter and absorbing it in the summer. This forces mechanical HVAC systems, heating, ventilation, and air conditioning, to run continuously to maintain a stable interior temperature. We are currently constructing static, rigid shapes designed for a climate and energy landscape that is no longer predictable. The GeneCapsule blueprint addresses these inefficiencies by treating a building as a closed-loop system rather than a terminal point for resources. To improve long-term efficiency, we must shift away from buildings requiring constant external inputs and towards structures designed for environmental adaptation. This exploded view schematic illustrates the GeneCapsule blueprint. It functions as a technical framework that organizes the structure into 3 intersecting functional layers: materials, energy, and water. The gene aspect of the framework refers to the specific physical characteristics a building inherits based on its environment, allowing it to function efficiently in its specific climate zone. Instead of shipping in virgin raw materials, the framework prioritizes locally sourced, regenerative, or recycled components to build the primary structure. The primary method for reducing energy demand is passive design. Passive design is a strategy that uses the building's orientation, windows, and walls to manage heat and light naturally without using electricity. This graphic demonstrates orientation. By aligning with the sun's arcing path, the structure captures winter warmth and provides summer shade. In this cross-section, cool air enters low vents, warms, rises, and escapes through a roof exhaust, creating a natural cooling cycle. By engineering the building to use environmental forces for heating and cooling, the GeneCapsule significantly lowers its baseline power requirements. While the gene mechanics handle the exterior shell, the capsule mechanics focus on internal systems that allow the home to operate as a self-sustaining unit. The structure is equipped to generate and store its own electricity from local renewable sources, like solar or wind, to power all internal appliances. This cyclical flowchart shows how the water loop works. Rain and household water are collected and passed through an integrated biofiltration layer, a system using natural biological processes to clean water, before being routed back for non-drinking uses like irrigation or flushing. This localized efficiency provides a layer of security, as the home remains functional even if the external municipal water or power grids experience a failure. The internal mechanics are modular. This means technical components like batteries or water filters can be removed and upgraded individually as technology improves, without disturbing the rest of the house. Integrating these systems allows the home to function as an autonomous unit, providing consistent utility with a fraction of the traditional environmental cost. When we take a macro view of this framework, we can see how these units scale. This rendering shows an entire neighborhood where modular capsules are integrated directly into the local landscape. These units can be linked into a microgrid. A microgrid is a localized power network that allows neighbors to share energy. As this map shows, water and power move horizontally between houses, allowing one unit surplus to support another. This decentralized network ensures that the community stays powered even during extreme weather events that typically shut down centralized power plants. The goal of the GeneCapsule blueprint is to move architecture toward a model where buildings contribute to the local ecosystem by filtering water and sharing renewable power. Because the system is based on standardized parts, it is highly scalable. Modular components, like the one seen here sliding and snapping into a structural frame, can be manufactured off-site and deployed quickly. This framework is the starting point for our work here at GeneCapsule. Subscribe to follow along as we test these designs and explore new methods for sustainable engineering. The long-term viability of our cities depends on replacing linear resource consumption with the integrated engineering shown in this blueprint.